Hello, everybody. Good morning or good evening, depending on where you are, and welcome to this lecture, which is an informal introduction to the study of calculus and the study of derivatives. And we will do this by studying limits. The first thing before we discuss limits, I wanted to give you a simple example. Let us assume that we want to prove that 0.99999 is equal to 1. First of all, how many of you think that this is actually true? Or how many of you think I'm going to use some trick to actually prove that this is true? Because I'm sure you've seen in many books there are pseudo proofs to prove that 1 is equal to 2 or 5 is equal to 10,000. And such kind of proofs can be done via some tricks. Do you think I'll be doing that, or do you actually believe this to be true? 0.99999 equals 1. Somebody's saying there is a trick, but not a pseudo one. Okay. So you all know what is pseudo, right? Pseudoscience and all of this. So it's like fake, not fully fake, but make believe sort of thing. I don't think there's any trick here. This is actually true. The thing is 0.99999 is actually equal to 1 if it goes all the way. If you stop it at any point of time, then it's not equal to 1. Even if you run this for, let's say, from the beginning of the universe till now, if you run this 0.99999, right, maybe you'll have like Google nines. That will still not be equal to 1. It will only be equal to 1 if you run it forever. And the thing to note here is that 0.88888, this thing is not equal to 0.9. This is true only with respect to 0.999 being equal to 1. Okay, so let me take Venkatakrishna's suggestion. Let's say that x equals 0.99999. Okay, so I will do something very simple. I'll do 10x. 10x will be equal to 9.999999 because I'm just multiplying it by 10. It will shift by 1 decimal place. Now I can subtract the second equation. So I can subtract the first equation from the second equation. So that will give me 9x equals 9, right? Because if I subtract 9.99999 and 0.99999, all the 9's get cancelled. So you get 9 minus 0 is 9, which would then imply that x equals 1. So we just started off by giving x to be 0.999, and then we conclude that x is equal to 1 because of the simple operation. Now, this is how we would prove it using number theory, kind of. Not number theory, just using some arithmetic and some tricks in algebra. There's a way to fundamentally understand what this equation means. And I will write it in the language of calculus and in the language of analysis. We say 0.99999 tends to 1 we say tends to 1 as number of 9's tend to infinity. You might recollect from an earlier lecture that we had, I think 2 months ago. We spoke about limits, right? I kind of explained to you what it means for something to approach something. Or when we talk about an upper bound or a lower bound, right? We did those graphs and we spoke about what is the lowest number that will be bigger than our entire sequence. What's the largest number that will be smaller than our entire sequence, things like that. So as you increase the number of 9's, it approaches 1. So let's see what this means. This means that, so let's say I have 2 columns here. On one side I have 1 and another side I have the 0.99999. Do you agree with me that if both of these are same, then when I subtract them, I should get 0 if they're equal? If 1 is equal to 0.999 and I do 1 minus 0.999, I should get 0, right? So what we will say is, rather than dealing with 0.999 infinite number of times, that's very difficult to talk about, right? We don't know how many 9's there are and it gets a little tricky. We will say, and we will look at this strategy. We'll start with comparing 1 with 0.9. Then we will compare 1 with 0.99. Then we will compare 1 with 0.999 and so on. And we will see what will happen. Okay. So if I compare 1 and 0.9, I have 1 minus 0.9 equals 0.1. Next, if I do 1 minus 0.99, I get 0.01. If I do 1 minus 0.999, I get 0.001. And this keeps going on. Okay. So now it's easy because all we have to show is that this thing on the right will approach 0. If the thing on the right approaches 0, we are done, because the thing on the left is exactly what we were initially doing, that's subtracting 0.99999 from 1. And we can clearly see that it approaches 0. How do we prove that it approaches 0? We prove that if there is any number between 0 and one of these numbers, I can find another number in between that. So basically what I'll prove is that this number will get as close to 0 as I want. There will be nothing left in between. The moment I find something, so for example, if I draw it on a number line, if this is 0 over here, and here I have 0.1, and here I'll have 0.01 and things like that, I'll keep getting closer and closer to 0. So what I say is, even if you find a point that is as close to 0 as you want, I will be able to find a number from my sequence, that is the difference of 1 and 0.999, which is nearer to 0 than your number. Basically, there's no number which you can find in between my sequence and 0, which then implies that my sequence has to go to 0. Because if my sequence was not going to 0, there had to be something else in between. But no matter what number you find, even if you find a number here, I can find a number here. If you find a number there, I can find a number here. If you find a number there, I can go even closer to 0. Maybe I will never reach 0, theoretically. Probably I can never show you when I'll reach 0, but I can show to you that no matter what you give me, I can go closer to 0 than that, which will basically mean I win the race and I get to 0 before anyone else does. No one can get to 0 before me. So that implies that the difference is going to 0, and 1 minus 0.999 goes to 0, which implies that 0.999 is equal to 1. Okay. Now let's write some limit related things in a more formal way. We say limit x tends to a f of x. This is something in which 3 different things are going on, and this is something very important to understand when we talk about limits and calculus and all of those things. What does this notation actually talk about? So there are technically three different things going on in this. Can people point out the 3 main things going on in this one expression? I won't call it an equation. It's not an equation. Equation is only when there's a left hand side and right hand side and they're equal. Let's see. So first thing we notice that there's an f of x. Let me circle it in blue. Right? What is f of x? It's a function. And we have talked enough about functions in our last class and before that, and I think 3 classes before that. We know what's a function. We know that x is going to be inputted into the function and we get an output. And we know a lot of things about that output. We know that output has to be well defined. We know that it's not going to be something over 0. We should know that this f of x should only be 1 value. It cannot be 2 values, because remember, the function is going to output only one thing. There was a very good analogy that one of my professors in India long back had told me, and I wish to share it with you. A function is more like matching the people in the world to their heights, right? So let's say you map everybody to their height. I'll be mapped to 6 feet. Somebody else will be mapped to 5 feet or whatever. Now, many different heights might have many people. Like for example, the height 5 foot 8 inches might have more than 1 billion people in the world who have that exact same height. But there will not be any person who has 2 heights. So one person will be mapped to only one thing. But there could be many different people being mapped to the same thing. So then we talk about one-to-one function and all of that. But in general, a function allows many different things to be mapped to the same thing. But one thing will be mapped to only one thing, basically. So we know that f of x is unique with regard to x. That's the first thing. That's the first bit of information that we can get the moment we see this equation, that there is a function. The name of the function is f and it's on the variable x. Second thing we are seeing here, let me circle it in green, is x tends to a. What does this imply? This implies that there's another number a. By the way, these are all numbers, right? X, a, and all these are numbers. They cannot be abstract quantities or some variables. I mean, they could be variables, but they are denoting numbers. They're not denoting alphabets. They're not denoting other functions. Those are numbers. So if we write x arrow a, then it implies that as x is approaching A. So X is getting closer and closer to A. That's what it implies, right? X is getting closer and closer to A. Do you understand what's going on? So the first thing is there's a function f of x. The other thing is x is approaching something else. So basically you can kind of think that what we're doing at this point of time is we have a function, we have a variable x, and we are seeing what happens to that function as this variable approaches something else. Okay? And thirdly, and most importantly, is this word over here, which is LIM, which is limit. Probably the single most important word in all of real analysis and calculus. Limit. So let me read this expression out to you in order. How one would read this? We would read as limit as x approaches a f of x. So we wish to calculate what happens to f of x as x approaches a. We wish to understand the limit of f of x as x tends to a or x approaches a. Why is the word limit important? Why don't we just say x goes to a, f of x? Why don't we just stop it at that? Because f of x might not exist so easily. It might not be something that we can grab hold of. It might be something that we can only guess. It might not be a simple function which we can quickly say, oh, when x goes to a, this function will go here. No, it might not be that simple. It might be something that approaches something very slowly. And we might have to study the behavior of the function and kind of make a guess saying, when x approaches a, f of x will approach something. The limit of f of x will be something, which means that is where it will finally reach. You know, we say we cross the limit of something, right? Or you say, this is my limit. I cannot go beyond this. So what does that mean? There's some sort of a line which it won't cross. That's what it means. So we can kind of predict where f of x will go closest to which it will not cross. Let's look at a simple example. And I'll give you a silly example. Just in case you're feeling this is something overwhelming and something very complicated, you're saying in one expression, there are three different things. What in the world? Let me actually tell you that this is very silly. And we've been doing this since probably we are 4 years old. It's just that we are now giving it a different name and explaining it very, very systematically. If I was to write limit x tends to 3, let me actually write that properly. If I write limit x tends to 3, x plus 1, this is 4. Addition, 3 plus 1 equals 4. Assuming all of us know that. It would be a sad day if we don't know that. So 3 plus 1 is 4. Now don't ask me which base and is this binary. No, simple decimal 3 plus 1 is 4. But when we say 3 plus 1 is 4, we're taking things for granted. When we learn it in maybe kindergarten or first grade, we say 3 plus 1 equals 4. Say 1, 2, 3, 4. But how do we know that there's nothing in between? How do we know that 3 plus 1 is 4? What is 1? What is 3? Who gave us the right to say that if you take 3 and if you add 1, you'll get 4? How do you decide on that? We don't know what is pi plus e plus root 2 plus infinity minus negative 1 square root raised to the power Euler phi function divided by the Riemann zeta function. We cannot predict what that is. So who told us what is 3 plus 1? Can we see 3 in nature? No. We can see examples of 3. We can say that there are 3 trees over there. We can say there are 3 fingers on my hand. But what exactly is this 3? It's not the number 3, because if I say this is 3, this is what is 3 in English, or when I write it using the way of writing that we write now. If I write it like this is 3 in some other language, or if I write it like this, it's 3 in some other language. We don't know. So we cannot use symbols to explain these numbers. We have to be very careful. So when we write limit x tends to 3, x plus 1 equals 4, we are actually giving the best possible explanation to that phenomenon. We are explaining what is 3, we are explaining what is plus 1, we are explaining what is 1, and we are explaining what is x. How do we do that? So we are saying if on this number line, which has infinite number of numbers, right? Infinite numbers, we don't have to define what is 1, 2, 3, there's everything. There's all possible quantities from minus infinity to plus infinity. It's the real number line, right? And there are ways of proving why it exists, and we can prove that between any 2 points on the real line, you can find infinite number of points, and all of that we've done. Like we did it in our functions class. So this equation implies limit x tends to 3x plus 1 equals 4 implies that on this number line, if you define a point to be 3, when you get closer and closer and closer to that point, and you jump one step ahead of you, you will get closer and closer to 4. So as I approach 3, now I'm waiting for a question from somebody here, but let's see if somebody will ask that question. As I approach 3, if I add 1 to 3, I will get 4. I'm waiting for you to ask me a very important question here. I'll give you a hint as to what question you are supposed to ask. The hint is approaching 3 how? Look at the number line. What do you think could be the confusion here that we have to address? Any thoughts? Good. Somebody says from the left. Aha, that's exactly what I was looking for. Who told you that we're approaching it from the left? Okay, first of all, we cannot approach it from the top or bottom because there's nothing over there. So there's only two possibilities. There's a two-dimensional, one-dimensional number line. Not one dimension. Is it two-dimensional? It's one dimension. It's one dimension. It's just one line. We can either approach it from the left side or the right side. How are you sure that we are approaching it from the right side or the left side? Why are you saying it's left? Why not right? So you're saying if we approach it from the right, then 3 plus 1 would not be 4. You're saying 3 plus 1 would be 4 if and only if we approach it from the left side. How many of you feel we're approaching 3 from the left side, and how many of you feel we're approaching it from the right side? Just send me the message as to what you think. Left or right? Ruhi says left. How many of you agree with that? Okay, somebody's asking a very important question. Does the side from which we approach matter? 100% it matters. 101% it matters. In fact, if we are not careful which side we're approaching from, we can destroy half of mathematics. Not with regard to this function, but with regard to many functions. We should be very, very careful as to which side we approach it from. In this function, it doesn't really matter because it will still be 4. It will still be 4. Let's see why. Let's look at some examples. Let's say we're approaching 3 from the left side. So let's start at 2.5. 2.5 plus 1 is 3.5. Okay, let's approach 2.7. 2.7 plus 1 is 3.7. You're getting closer and closer to 3, and we're also getting closer and closer to 4. 2.9 plus 1 is 3.9. 2.95 plus 1 is 3.95. 2.955 plus 1 is 3.955. 2.999 plus 1 is 3.99. So it's kind of clear that as we get closer and closer to 3 from the left side, we are approaching 4. But we could do the same thing from the other side. Because if I do 3.4 plus 1, I get 4.4. But if I do 3.3 plus 1, I get 4.3. 3.01 plus 1 is 4.01. So as I come closer and closer to 3 from the right side, it still approaches 4. Right? So we are good either ways. That is why I have written it like that. I've written it as limit x tends to 3, x plus 1 equals 4. Suppose it was true that only from the left side it is approaching 4, then I would write it like this. There would be a minus sign on 3. This is a new thing. I don't think anyone here has seen it before. If it was approaching 4, I would write it like that from the left side. If it was approaching from the right side, I would write limit x tends to 3 plus. So that plus or minus at the top of 3 will tell us from which side it is. If I don't put anything over there, then it means it's approaching from both sides. I did not put that plus or minus sign in the initial expression because I thought you might leave the class if that happened. There will be 4 different things in one expression, right? First of all, we're having a difficulty dealing with 3 different things, and let alone do 4. So that minus or plus sign, remember the minus or plus sign is at the top. It's a superscript, because if you put it behind 3, then it would be minus 3, right? It's a negative number. If you put it at the top to imply from which side when you approach 3, what will happen. Somebody saying, is it a convention to approach from the left? No, it depends on the function. one function might be defined in such a way that for when you come from the left side, you get one answer. When you come from the right side, you get another answer. You might have to think of such an example, but I'll not give it. Okay, let's do some simple exercises. Can you all solve this? So the first question I'm giving is limit x tends to 5, x plus 2. Okay, want to give me the answer, type it in the chat. Second question is limit x tends to 1, x times 5. Okay, and lastly, limit x tends to 2, x squared minus 4 divided by x minus 2. Let's start with the first question. Can you all type the answer to the first question? What happens limit as x approaches 5? What happens to x plus 2? As x approaches 5, what happens to x plus 2? 7. Good. Good to know that at least one person here knows addition. I'm waiting for answers from the other people. Limit x tends to 5, x plus 2. What happens to that? What is x plus 2 as x approaches 5? No answers? Guys, what is 5 plus 2? I have 3 answers. Okay, now I'm getting more answers. 5 plus 2 is 7. Very nice. What happened to the other 5 people? Okay, good. So x plus 2 approaches 7. That was not that bad. Let's look at the second question. As x approaches 1, what happens to x times 5? 5. Good. You all know your multiplication tables. 1 times 5. How many of you feel that the third question has an answer at all? Look at it very carefully. How many of you feel that the third question actually has an answer? Look at it very closely. Or do you see some problem there? Do you see a situation where something looks a little fishy? We are having x squared minus 4 divided by x minus 2 as x approaches 2. If x is equal to 2, is that defined? Let's directly substitute x equals 2. We'll get 4 minus 4 divided by 0. Oops. Division by 0 is illegal. It's out of bounds. So can we have a solution to that third question at all? As x is approaching 2, what happens to x squared minus 4 divided by x minus 2? I can see a few people getting impatient in the chat, but I'm just waiting for everybody to look at this and understand why this is a problem. Somebody's saying here x tends to 2, x is not 2. Good point, but if we are saying x is approaching 2, will it not reach there someday? And when it reaches someday, won't all hell break loose because we're having 0 divided by 0, which is the worst. First of all, having a division by 0 is terrible. But if you have 0 divided by 0, then you are completely gone because you could literally have any answer possible. So 0 divided by 0. So I want to make this clear, guys. 1 divided by 0 is not defined. Okay. Or 20 divided by 0 is not defined. But 0 divided by 0 is worse than not defined. It basically is anything that you want. Any answer that you want is correct for 0 divided by 0. If you want 0 divided by 0 to be 10, you're right. If you want 0 divided by 0 to be minus 20,000, you're right. If you want 0 divided by 0 to be I, that's the square root of minus 1, you're still right. Because basically anything you multiply by 0, you get back 0. So 0 divided by 0 could technically be any number in the universe. So what will happen when we reach there finally? Because when x approaches 2, we'll have 4 minus 4 divided by 0, which is the problem. Aha, I see some people suggesting me to breach this illegal business by doing a trick. So the trick here is to factorize the numerator. But let's, before we get into that, let us actually write down a few values. I'm going to use a calculator here to give you some accurate data. So what do we have here? We have x squared minus 4 divided by x minus 2, right? This is what we have to calculate as x approaches 2. So let's make a table here and let's have a x value here, and here we'll have, let me call this as y, and we'll have y. So y is this whole thing, like y should be the answer to x squared minus 4 divided by x minus 2. If x is equal to 2, y is not defined. We don't even know what y is. It could be anything, because if x is 2, then this is 0 divided by 0. Let's see if x is close to 2, what happens. Suppose x is, in fact, give me a second. I'll make this interesting. Let me actually write a short code for this, and let's run the program, and we will see what eventually happens. Okay, just give me a second. Actually write it. If you wish, I could, no, if I share my screen here, then I will not be able to share my phone screen. So let me first type this out, and then I will share my screen. So what I'm going to do is I'm going to start x at 2.5. So let's do a poll. Do you guys want it to see it approaching from the left, or do you want it to approach from the right? Let me do left, actually, that's better. Let us approach from the left, and we'll start at x being 1.5. And each time I will increase it by half of the difference from 2. So basically, when it's at 1.5, in the next iteration, I'll make it 1.75. Okay, so I'll bring it closer to 2. Then in the next iteration, I'll bring it between 1.75 and 2. So that way we get closer and closer to 2. Okay. I think this should be ready. Just give me a second. Okay, good. So let me share my screen now. Okay, is it visible, guys? Can you see this one? Let me actually make it full screen. I think there are some pictures of my book release in the background. So let me actually share only the Python code. Just a second. Okay, so you're able to see this. Let's start at x equals 1.5. And then I have written this program over here, because this is just going to print x squared minus 4 divided by x minus 2. And then it will increase x to something closer to 2. So let's see what happens if I run this. Okay. Looks like it reached 4. So it started off at 3.5, then it went to 3.75, then it went to 3.875, 3.999, and get closer and closer. And eventually, it has now reached a point where even the computer doesn't know the difference between this and 4. So it's just saying, let's approximate it to 4. And then it is saying it's 4. And then finally, it's saying 0 division is not allowed. because what happened here is now this has gotten exactly equal to 2. Although this should never approach 2 in reality, because we are dealing with a machine, it will have its own error. And when you talk about, for example, if I do 1.999999999 like so many number of times, it will get very, very close to being 2. So if I just say what is x equals, if I keep doing this, then eventually at some point of time it will think it's 2, because it would have reached a point of time where it's beyond its shortest error. It won't be able to differentiate between this number and 2. I don't know if this is good enough to reach there. Yeah, see, it says if I defined x to be 1.999, it says, I ask it what is x, it says it's 2.0. Okay, so that's that. So now we saw from the computer that it's approaching 4. But are we convinced mathematically that it should approach 4? Yes. So now let's do the factorization and realize why it's approaching 4. Now let me start sharing my screen again. I will answer all your questions soon. Okay. So we see from the code that as x gets closer and closer to 2, y gets closer and closer to 4. Although x will never reach 2, y will never reach 4, it will get close enough. So how do we solve this mathematically? We just have to factorize the numerator. When we have x squared minus 4 divided by x minus 2, what we do is we just write this as x plus 2 times x minus 2. And then we divide it by x minus 2, and then we cancel these things out. So we have x plus 2 remaining. And now we can easily do x plus 2 as x is approaching 2. It's going to be 4. You might ask me a question as to how was I allowed to do the factorization if it's approaching 0, right? If it's approaching 0 divided by 0. The thing is, when we do the factorization, we're not really dividing by 0, because we don't know what is the value of x at this point of time. We're just doing it assuming x is something. And if x is something, as long as x is not exactly equal to 2, this factorization is well defined. So once we have done this factorization, then we have the, what do you say? We have the permission to get very, very, very close to 2. And that gives us 4. Okay. So that is with regard to limits. And maybe I will give you more problems to solve in the next class, but today I want to talk about a few more concepts. So we will do problem solving with regard to limits, which will be slightly more complicated. It won't be as simple as directly looking at it and doing factorization. It might involve you to do a few more tricks, but I'm sure you'll be able to do it. It's simple algebra eventually. Let me explain to you what is the meaning of slope. This is fundamental in understanding a lot of things. So if we have a graph, okay, if I have a graph, what is the slope of this graph? How do we define the notion of slope? Now, when we use it in colloquial way, like when we use it in our day-to-day life, we say, I was running up the steep slope. Or you say that when I slid down the slide, the slope was not that steep, so I wasn't scared. So we kind of use it in all kinds of situations when we talk about slope. What exactly is this slope? First of all, let's test our intuition. All of you to look at the screen, which has a bigger slope. Okay, this is a slide. This is not a triangle. This is a slide, the playground thing that kids play on. Let's actually draw it in a slightly different way so that we know what it is. There's a kid over here. Okay, then there's this slide. This is A and this is B. Which slide has a bigger slope? Let's see what you guys think. Which slide has a bigger slope? Somebody's asking, do you mean lengthwise? That's a good question. Why do I care about length? I'm talking about slope. Is slope length or is it? We're saying B has a bigger slope. Okay. Intuitively, when you look at these two slides, let's say we don't even know what their length, breadth, it doesn't matter. Which has a bigger slope? Which looks a little steeper? It's B. Good. And suppose I was to draw a legendary slide. Let's say this is the, let's say, first of all, we have the worst slide in the world. This is the worst slide in the world. Okay. This is the worst slide in the world. And it is so much, it's such a flat slide that you have to literally apply oil to skid down it. It's not possible. The friction is too much. It's the worst slide. And now let's see, there's the best slide in the world, newly built and highly recommended, highly not recommended for anybody below the age of, I don't know, 18, whoever has a faint heart. This is the slide. Okay. So now we can see that this has a bigger slope. This is very steep. Can you suggest to me or think intuitively what is having the worst slope possible in the world and which will have the best slope possible ever? They might not be, we might not be able to create them. Maybe we can create them. I don't know. Okay, good. So this line over here will have the worst slope ever. This one, not the slide that I drew. That is still not the worst. I could make it. The line which I drew below that has the worst slope ever. Look at that. It's just a straight line. It's a 180-degree straight line. And the best possible slope is this straight line. I'll tell you something that's very incredible. The slope of that yellow line which I drew is 0. We define the slope to be 0 over here, and the slope of this line is infinity. Infinity. Really, it's infinite. The slope of that straight line is infinite. And you might be wondering, okay, so maybe then slope is only defined to be 0 or infinite. No. If I start off here, let's start off here. Actually, let me start off. I don't want this. Okay. This slope is 0. This is slope 0. Gradually keeps increasing. The line which we define to have slope 1 is this line. This line is having slope 1. Okay? 1. Slope 1. And it is the line which is 45 degrees to the x-axis. That line has slope 1. And then we keep going up and up and up and up. And basically at this point of time, you can access any number that you want. There's 100, there's 1,000, there's trillion. And when you finally have this straight line perpendicular, it has slope infinite. So what exactly is this slope? How do we calculate this? Who was the one who decided that that has to be slope 1? Surprise, surprise, the slope of a line is defined using tan of x. Our good old friends trigonometry finally make their heroic entry into our calculus class. Tan of x is the slope of a line. If x is the angle where the line meets the ground. So let's draw a graph. This is our graph. My x-axis over here. My y-axis over here. And this is my, let's not have all those other additional things. And this is 0. So the line on which we measure the angle to which it's intersecting is the x-axis. It's convention. We could do it the other way around as well, but it's always good to see because we want the slide to start off at 0 where it's parallel to the ground and then it gets bigger and bigger. So if I was to draw a slide over here like this, okay, the length doesn't matter. So the thing to notice here is this is a big slide. Let's draw a smaller slide with the same slope. So let's say that slide goes over here and it ends over here. It's a smaller slide. Both of them have the same slope. Exactly the same slope. No difference. Because remember, the trigonometric ratios do not change if you keep the side ratios the same. If you increase the size of the triangle, it won't change the trigonometric ratios. Because the trigonometric ratios are dependent only on the angle. That's why we defined them like that. That is why we gave them names depending on the sides corresponding to the angles so that we do not have ambiguity. That's the sole purpose of that lecture the other day where I told you that we should be able to define things universally. We cannot say side A, side B, side C. Okay? So this green slide and the red slide both have the same slope because their angle that they make with the x-axis is exactly the same. Let's draw another slide. It's slightly bigger. Let's take it all the way till here. It also has the same slope. So now how do we calculate slope? Does anybody remember the formula for tan? How do we calculate tan? Let's make it interesting. Let's say we don't know the what is that? We don't know our angle. Let's say we don't know the angle. It's opposite divided by adjacent. Very good. I am happy that you remember that. So if we were to calculate the tan of this angle, we would have to do, so for all the slides, it would be the same because the ratio remains the same because the angle is the same, but let's pick the red slide. If I know this value over here, let me call it A. This is the length, the height of the slide. And this is B, which is the width of the slide. My tan will be A divided by B. Okay. Tan will be A divided by B. And that is exactly the slope of this slide. It's A divided by B. So any slide you want to measure its slope, you look at its height from the ground at the point where you want to measure the slope at, and the distance to that particular point, the distance on the ground, you divide them both, A divided by B, opposite divided by adjacent, and that gives you tan. Tan theta is the slope of the slide. Now let us see why that line which I defined, the 45-degree angle, why does it have slope equals 1? So let's draw that different slide. Let's keep these slides here because I want to compare them. So that slide will have 45 degrees, right? So it will look something like this. Do you agree with me? The angle will be 45 degrees. So now using the properties of the isosceles triangle, we know that if one angle is 45 degrees, the other angle should also be 45 degrees. So now we know that this is 45, we know this is 45, which then would imply that this side is the same as this side. They have to be the same because they are opposite sides of the same angle, right? We all know that from triangle, from high school, that the side opposite to the greatest angle will be the largest side, the side opposite to the smallest angle will be the smallest. So in this case, both the sides are opposite to 45 degrees. So they will both have the same length. So A divided by B in this case will be 1 because A and B have the exact same length. So the slope of the slide with 45 degrees is 1. And this slide can be as big as you want. It will always have the height equal to its base. That's why back in 8th grade or something, when we had to calculate the area of a triangle, I would love it if it's a right angle triangle, which is isosceles, because we can just do, instead of doing half times base times height, we can just do half times base squared or something because the base and height are the same. So now the last question which I will address before I end is, why is that straight line having slope infinity? So is the tan function taking an infinite value at some point of time? Yes, it does. But we'll get into this proof very carefully next time. But I just want to give you the intuition as to why that's infinity. Let's get back to our good old graph. So we have this slide. We have a slightly bigger slide, and all of that is done. Let's say we have a constant function over here where the slope is 1. I didn't do a good job drawing it, but assume this is 45 degrees. Now, what happens to that steepest possible slide? To understand it, let us actually go to a slide which is slightly not exactly straight line. Let's go, because that is so hard to imagine a slide which is like just straight line, because how does it even have a height? Let's look at this slide, a very, very steep slide. Okay, so we have an extremely steep slide over there. So we have an angle over there at the base. I'm sorry about this drawing, but I think you can kind of visualize that's a slide, very steep slide. This is the top of the slide over here, and this is the height. Now, if we look at the tan of that angle, we do the opposite over the adjacent. The opposite side, let's say this is 100. Okay, this is 100. The opposite, the height of the slide is 100. And let's say this base is about 5. Looks quite accurate, right? It's 5 versus 100. So now if I did the tan, I would get 100 divided by 5, which would be 20. So the slope of that slide is 20. So we went from slope being 1 to slope being 20. That's an extremely steep slide. I think so all of this is extremely useful when we construct roller coaster rides and all of that, right? If you have a slide, like when you go to, let's say you go to SeaWorld or you go to Wonderla or something like that, and you have this water slide, they have a limit as to how much the angle of inclination should be. Because if it's beyond a point of time, it could be fatal, because that boat might not slide, it might just fall because gravity will pull it down. So this kind of slide would be illegal in any amusement park, the one which I drew in blue. Maybe the best slope we can get is somewhere maybe 1.5 or 2 or maybe 2.5 might be fine. I don't know. I'm not a architect here, but something like that. So this slide has slope 20. So how do we get to infinity? Imagine a slide which is a straight line, basically. So it's just going up, 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 up. So we don't even know at what point of time we can find its height, draw a line to the base, and measure the distance to the base. Because the base itself is so small, like it's so small compared to the height. Almost. The height is a straight line. So how do you even get on top of the slide? So then what it becomes basically is the height gets very close to, the base gets very close to 0, and the height gets very, very close to infinity. So then when you divide them, you get infinite. It just goes beyond anything. As it approaches infinity, it's a limit, by the way. We cannot really talk of a slide which is having that, but you could potentially, so if you want to create this slide on your own, there's a simple way to do it. Let's say we want to create a slide of slope 1000. So how would we do it? We would first draw a line over here, which is of length 1 centimeter. Okay, say a line of 1 centimeter. Now we will draw a line over here, which is of length 1000 centimeters. 1000 centimeters. We can just keep it going forever. So that will be like 10 meters long line. So let's say this is 1000 centimeters. And then if we try to connect this over here, that slope will be 1000. But this is a very bad approximation. Here, I think the slope is 10 or something. But if you are actually, just think about it, right? If we were to scale this image a little bit, so if I have this 1 over here, the 1000 might be somewhere over here. So when I actually do the slope, it might be so close to being a straight line, right? I hope you're getting the picture. So that way we can have a slide with a slope as big as we want, and eventually when it's just a straight line, it's going to be infinity. Okay, so that is that. We will study more about slopes, and then we will bring in our study of limits to understand actually what calculus is all about. Calculus is all about studying 3 different things: limits, slopes, and area under graphs. This is basically calculus in 3 lines. Everything to do with calculus comes under these 3 things. Completely. There's absolute, I'm not even exaggerating. Anything. So when we study about functions, we'll study the limit of the function. We'll study the slope of the function. So we'll draw the graph of the function, and then we'll see what is the slope of that graph. Remember, all the examples that I gave you were with slides, because slides have the same line. What if we have a function like this? What is the slope of this function? Right? So it gets extremely complicated. How do you calculate the slope of that? The slope will keep changing at different points. At this point of time, the slope might be very nice because it doesn't look like a very steep line. Over here, it's going somewhere ridiculously crazy. It's going the reverse way. And so things get crazy. So we have a function. We look at its limit. We see where it goes. We look at its slope. We see when we draw the function on a graph, we'll see how tilted it is or what is the slope. And then we'll calculate the area under the graph. That's integration. We look at everything, and then we say how much area is under this entire graph. When I draw this graph over here, what is the area that the graph has covered under it? That is the study of calculus, all these 3 things. So we will revisit limits next time, and we will also study slopes with slightly more complicated examples. And let's go on this beautiful journey of studying calculus. Thank you so much. I'll stop the recording now, and I'll see you all next week.